Okay, so let me start that over. Okay, so basically we're gonna just start with covering NumPy. This is for the recording. I already did this. I'm gonna apologize. And so there's a bunch of different ways you can create your NumPy matrices. You can create random normal Gaussian elements. You just apply the shape. You can create a random uniform. So these random things are actually pretty good for just testing your code if you just want to try it out on something. And so you just generate random matrices, and then make sure that your code actually works and all the shapes match and everything. You can create all ones, you can create all zeros, you can create an identity matrix. These are all dense, so these are not sparse. And the same thing, you can, in addition to matrices, you can make vectors. Okay, so you just supply one dimension. It'll be a one-dimensional NumPy array, and the same operations work here. Random vector, vector of ones, vector of zeros. NumPy.arange will give you, it's like the Python range, but it's now just wrapped in a NumPy array. So, and then here's one that you might find useful for the cross-validation is the NumPy.random.permutation, which will give you a random permutation from 0 to n-1. So when you're doing cross-validation and you want to give it a random permutation, you can give it something like that. Okay. So you can cast your arrays as something different. So for example, you can just use the as type command to change it to an integer or like a Boolean or a float, whatever you really need it to be. There's basic accessing elements in the array, which is you just supply it the number of indices equal to the number of dimensions. So for this assignment, you're not going to go past 2 dimensions, but if you really wanted to make a 3-dimensional or 4-dimensional NumPy array, you could do that and give it 4 indices, and it'll pluck out the elements corresponding to that. Also, please interrupt me if there's any sort of question or anything. Okay, so in addition to integer indices, you can give it a slice. I'm sure most of you are familiar with this. The slice, you give it a start, an end, and a step size. Or if you give it none of those, then it'll just slice everything. So it'll get the entire thing. So in this example, it'll get the, it'll take every single column entry of the 0th column. Okay. Actually, something that's not here is that you can also do accesses via a list of indices. So you could do A of 1, 2, 4, and that'll pluck out. So this will pluck out the first, or not the first, the 1th column, the 2nd column, and the 4th column, for example. Okay, so this is the 1, 2, and 4th column. Okay, does that make sense? You can pass a list of indices, and it'll index that list of integers into that axis. Yeah? Row. Yes, sorry, this is a row. Yeah, so this is the 1, 2, and 4th row. Thank you. There we go. This is what happens when I write it on the fly. Okay. And then you can do things like Boolean indexing. This will be useful when you're trying to query elements that meet a certain criterion. So, or in this case here, we just create a random Boolean, we create a random array of numbers, and we select the ones that are greater than 0, and then we can use this. This is actually just an array. It's an array of Booleans. And so you can just pass that array of Booleans as your index as well. This is not the same as a list comprehension, no. So, so yeah, the question was, is this the same as a list comprehension? It's not necessarily more efficient. It's better at different things. So a list comprehension will be good at creating things that are good at lists, which are unbounded, which remember are unbounded arrays. And so you're adding, if you're adding things to that list, you're creating a list element by element, then you probably want the list comprehension. But if all your elements are already created and allocated, then we have it in this array. And when you have everything already created and you're doing operations on the entire array at once, that's where these array structures start to excel better than the normal lists. So lists are usually good if you want to do something element by element with the list comprehension. But here we kind of don't want to do element by element. We just want to say, do operation on entire array. Yeah. So in this line, when we say, okay, we're going to take the entire vector and say we're going to get a Boolean vector that says that is true in all the places where the element is greater than 0. And then we're going to take this entire vector and index it into another vector to select all the ones where that occurred. Okay. And same thing, you can index. Oh yeah, he did it right. Yeah, you can. In addition to indexing with a list, you can index with an array. It's the exact same thing. Okay. All right. So here's an example, which is creating a one-hot encoding, which you'll commonly do in a lot of applications when you have a categorical random variable and you want to turn it into numbers. You actually did this on the previous assignment, but we just had you call, I think, Pandas's. Pandas had this command, I forgot what it was called, that just, yeah, that one. That turns your categorical variables into just like a 1 and in that column and zeros everywhere else. You can actually do that in pretty much one line in NumPy. So here, this is just creating a random vector of labels. So this, actually, why don't I just run everything instead of just yelling at you guys. Let's run everything. So, okay, so here we're going to have this B is just an array of labels. So, I just randomly generate an array of labels. And then what you do here is we're going to take this identity matrix, right? So this identity matrix of, is going to have each row of this identity matrix corresponds to a particular one-hot encoding, right? So each row of an identity matrix has a 1 in a particular position. And so what we're going to do is we're going to, as the first, we're going to take rows from this identity matrix corresponding to these labels. So this is going to take the second row, then the first row, then the first row, then the fourth row, then the second row, then the third row, then the third row, then the 0th row, etc. And then we're going to take the entire row, right? And as these, so if you think about this for a bit, you'll realize that this is actually just taking these labels and turning it into a vector of zeros with a 1 in the proper location. And then it does this for since we're using the list indexing, it does this for every single label. And it creates a one-hot encoding, which you can see right here. And so that's what it does, okay? So if you don't get it right now, just think about it a little bit and it'll make sense. Okay. So here's another thing that you'll find useful is that when you want to scale the rows and columns of a NumPy array, you can do this with actually more than two-dimensional, but it's easier to understand in 2 dimensions. And what they do is they'll take, so what they do is NumPy has this thing called broadcasting, where if you take a matrix and you multiply it by another matrix, then it'll try, without using the dot product, then it'll try to match up the matrices shape-wise to broadcast it onto the other matrix. So I realize in hindsight, what I just said is probably very convoluted. So what I'll do is actually, why don't we just visualize this example? So here we have actually let me run this. Yeah. So if we have A, which is just all 1s, okay? And then this here is this here is just a random vector, okay? And so what we want to do is we want to scale the elements of A by these elements, okay? And then so what you do is you just use this multiplication. So normally if these two things were the same size, then they would do element-wise multiplication. But now since this is a vector, it's going to take this vector, and so this is a row vector, and it's going to apply this to every row of A. Does that make sense? So we're going to do this multiplication, and it's going to multiply. So this row is this vector is the same size as the first row of A, and so it's going to take this vector and multiply it by the first row of A. Then it's going to take the same vector and multiply it by the second row of A. So we take this vector and we broadcast it on every single row, and this has the effect of scaling each column by the same number. Does that make sense? So then when you run this, it'll take this vector, multiply it on every single row, and then so every element in A is scaled by some number in this random vector.
If we did dot t to transpose that random thing, it would multiply with every column of A, right?
If it's the right size.
Yes.
Yeah.
Sure.
And if it's a two-dimensional vector, if it's a two-dimensional NumPy array. So in NumPy, if something is one-dimensional and you take the transpose, it's still one-dimensional. It's still a row vector.
Oh.
Right?
So transposing doesn't do anything.
Yeah. So transposing a one-dimensional vector doesn't do anything. So we could take this and transpose it, and we get exactly the same thing. So then, but then if we have, this thing here is basically inserting a fake axis, so that it now becomes this none here. So now if we take this and we do none, you see now it's a column vector now, right? So that's what this is doing. You can also do numpy dot, I think it's new axis, yeah. But none works too. So now that this is a column one, now this will broadcast across every column. And then so multiplying by this column vector will now scale every single row. Make sense? But yeah, if you take a one-dimensional vector and you try to transpose it, you'll get a one-dimensional vector. So then we take this guy and then transpose it, we'll get a row vector, but it's you can see it has 2 dimensions because it's wrapped in another list in the output here.
Is the none thing just like a hat?
The none is just I think it's a little nicer than typing numpy.new axis, but I guess it's a little not as clear. It doesn't really matter which one you use. Yeah, they mean the same thing. I think actually numpy.new axis might just be a variable that in numpy that is equal to none. That might actually just be it, but it might be a little more fancy than that. But yeah, it really doesn't matter which one you use though. You can use whichever one you want. Yeah. Any other questions? Okay. So here's something that's pretty important, which is you can do a bunch of matrix scalar operations. So if you're, if you want to broadcast, so broadcasting works by, how I said, it takes the dimensions and matches them up and tries to copy them over the matrix you're broadcasting onto. Now if you have a single scalar, that scalar is 1 by 1. So it can be broadcasted onto every single thing. That's how it works. Okay? So if you want to apply a scalar to an entire matrix, you do not need to create a new matrix that has the values that are all equal to that scalar. All you have to do is do the same operation just with that scalar. Okay? So I guess this is best seen in an example. Here we're just going to create a random matrix A, and then you can multiply the entire matrix by 3, for example. So this will scale every single element in the matrix by 3. This will divide everything by 3. This will add everything by 3. You can even call NumPy functions with a scalar, right? Most of them work with a scalar. So here you can take the minimum of every element in A with the number 1. So this would be identical to if I passed a numpy.ones and then put in n here. So then it's a new matrix of 1s that's equal in shape to the original A, but this wastes a lot of time and space, especially if it's very large. So I can just put a 1 there and it'll broadcast it to the rest of the matrix. Okay? So in particular, in your SVM problem, you're going to have to do some operations with max and adding or subtracting a 1. And so you definitely do not want to create a new matrix of 1s or 0s every single time you do this. It's just a waste of time and space. Okay. And then in addition to matrix scalar, you have this usual matrix, and matrix vector operations. So you can, you create your matrices, you can create your vectors, you can multiply them with the usual dot product using the function dot. Okay? So the important thing here is that this, if you want to do A times B, where A is a matrix and B is a vector, if you use the normal multiplication symbol, like this one, it'll broadcast. It'll try to do element-wise broadcasting. So instead, if you want to do actual matrix multiplication, you have to use the dot operation in NumPy. Okay? But otherwise, these work exactly as you would expect it to be from your normal linear algebra. Okay. And then otherwise, you have your typical element-wise operations, which is the same as broadcasting, just without copying, right? So it just broadcasts each element to each element. So you can take two equally sized matrices, add them together, subtract them, multiply them, divide them, and these will all do element-wise. Okay? So these operations are reserved for element-wise. You can also do things like numpy.exponential, which will raise it to e to every element in that matrix. You can do log, which will apply log to every element in that matrix. You can do comparisons, so this will give you a matrix of true-false booleans, where each element is determined element-wise of the two matrices. So it'll take aij and compare it to bij and compare them. And then here you can do tests on Boolean matrices. So you can do like numpy.all of a Boolean matrix, and it'll return true if everything is true, or false if something is false, or any is the other alternative, where it'll return true if anything is true, and then false otherwise. Okay? Make sense? Where A is greater than B. So turn that into an index. Yeah, so like query all the elements where A is greater than B. Yeah, so let's see if we can do that. So we have A greater than B. Let me run this. So then this gives us this thing, right? And then, let's see. I wonder if I wonder if this works. Yeah. So you can take all the elements where you can do this, which returns a Boolean array. I wasn't sure if this was going to work, actually, but turns out it does. So you can do this query, which returns a Boolean matrix that is true if A is greater than B, and then pass that as your index into an array, which will fetch you all those elements where A was greater than B. Okay? Was that what you're asking? Yeah. So then, this is pretty useful when you're trying to verify some property of your code, and then like maybe it must be true that A is greater than 0. Then you can Boolean, and you can make the Boolean array where A is greater than 0, and then index into your thing, and then see what's going on. So it's the type of thing that I would usually use it for. Okay, and then just a few more things. You can do a whole bunch of different operations with NumPy. I suggest you use them instead of coding them yourself. So for example, you can calculate the mean of a matrix, the max of a matrix, the minimum, the standard deviation. Argmax will give you the index of the largest element. So like a common thing that I saw in previous assignments was that most people were calculating the mean squared error by taking the sum and then dividing by the total number of elements. And then sometimes their answer would be wrong because they didn't put in the right number of elements. You can remove the potential for any kind of error here by just using numpy.mean. Okay? Then that'll always return the mean, and you don't have to worry about dividing by the correct number of elements. Things like that. So I highly suggest you use these functions. And you can also do things not just on the entire matrix, but on rows or columns of the matrix. So for example, this line here will give you the mean of every column. So by giving it an axis, you tell it which axis to look down. So the 0th axis is the column axis. The 1th axis is the row axis. And so saying numpy.mean A with axis equal to 0 means it's going to go down every column and calculate the mean. And then the result is a vector with the mean of every column. Okay? And then you can do this with all of the previously mentioned commands. And then let's see. Yeah, so then this is just another example where we recreate the one-hot encoding, and then by using the argmax with the access equals 1, so it'll take the argument maximum of every row. You basically turn the one-hot encoding back into its original labels. So does that kind of make sense? So we're going to take the, so A, remember A is our one-hot encoding. And then so now if we do numpy.argmax of A with axis equal to 1, then it's the index of the largest element in every single row, which is the original label. Right? So this is turning the one-hot encoding back into the original labels. That's all it's doing. Okay, so you can convert between these two pretty easily. You don't need to use like a for loop or anything. All right. Okay, last thing, second to last thing, you can compute block matrices. So you can take two matrices and put them into one matrix by using H-stack and V-stack. H-stack puts them together horizontally, and V-stack puts them together vertically. The only requirement is that the dimension that you're attaching them has to be the same, right? Otherwise, it doesn't really make sense. You can use BMAT, which allows you to pass a list of a 2D list of matrices, and then it'll put them together into one matrix. Though it very as you can see by this comment, it very annoyingly returns a NumPy matrix, which I haven't talked about, but might give you a bit of a pain if you ever run into it. So you have to cast it back into an array. Just a quick note on that is that NumPy matrices are basically in NumPy as legacy support for older versions of codes that rely on it. And the difference is that a NumPy matrix is confined to being two-dimensional, and that's it. Like you can't have a one-dimensional vector, or you could, but it would have to have a dimension of 1. It would have to have a dimension of size 1. And you can't have more than one dimension. And it doesn't work very well with the rest of NumPy. So it's really annoying if you try to like broadcast or if you try to do anything with a NumPy matrix, and then it gives you an error because it's trying to do what you would normally do in NumPy, but then it doesn't work because it's a NumPy matrix. So whenever you come up with like an error that you don't really know, double check to make sure that your matrix is not actually a NumPy matrix. Right? And then you can, so like if we take this guy here, I guess the first indicator is that you'll see that it says matrix. But just in case you don't see that, you can also just take the type of it, and it'll say that it's this matrix object. And so you want to avoid these matrix objects at all costs. Okay. It doesn't cost any time or space to convert them into a NumPy array, right? As array. So now it's an array. Right? It doesn't take much time because I think all it's doing is just changing the wrapper around the data. The data address is actually stored exactly the same, so it's there's no penalty to this. Any questions? Okay. Last thing is that you can calculate norms in NumPy. You use the linalg.norm. I think some of you have already used this. By default, without any arguments, it gives you the 2 norm. So then if you square it, then you'll get the normal squared 2 norm that usually you use. I think it's the regularization but the regularization that we use in SVM is also the squared 2 norm. So you might use it there. But if you ever happen to need a different kind of norm, you can just give it a different norm. So like the 1 norm is the L1 norm, which is the absolute value, and you can actually give it like any number actually, and it can do p norms for any number. I don't know if we'll need that. I think at most we'll need is the L1 norm, but just for your information. Okay. Okay. Any questions before we move on to sparse matrices? Okay. So your sparse matrices are super important because your SVM implementations are going to rely on them because we're going to use TF-IDF. I don't know how many of you have looked at the SVM assignment? Yeah. Okay. So like by now that you're going to be building an SVM on TF-IDF features, which we know from the last assignment is, or some of you, if you were in 388, you probably didn't do it, but it's going to be a massive sparse matrix. Okay. And if you actually look at it, I think it's over 100,000 features for each row. So if you try to initialize this matrix in memory, Python will at best crash and at worst crash your computer. So do not try to initialize this 100,000 by like 10,000 matrix as a dense matrix because it will not work on any kind of machine that you have. Okay. So this is why you need to use the sparse matrix formats. So we're going to go through, the same things here. Am I going too slow? Am I going too fast? Is this good? Okay. All right. So we're going to go back to basic array construction. So scipy.sparse has a lot more constructors than NumPy, mostly because they have a lot of internal formats. So they have like a diagonal format, they have the CSR, they have the CSC format. they have the LIL format, they have the COO format. In general, what you want to do is, if you're doing like math operations, you should probably stick to CSR or CSC. I think CSR is slightly faster for most of these because internally Python is stored in row format. But converting between these formats is linear time in the number of sparse elements. So you shouldn't worry at all about converting. So once you've built your matrix with like the COO format, just immediately turn it into a CSR format. So you can do that with just .csr. It's that easy. Okay. So just create your COO matrix. I think in this case, you just in the SVM problem, actually we just return it to you, so you don't have to worry about creating it. So just turn it into a CSR if it's not already, and or CSC if you really want to do that. There's not really a reason to. There's also these other constructors, which is sparse.I, which will give you a sparse identity matrix. And then there's sparse.diags, which will give you a sparse diagonal matrix where each diagonal element has the value given by a list that you pass to the constructor. Okay, so this will create a diagonal matrix where the elements are 1, 2, and 3. Okay, and then there's also sparse random matrices, which are almost the same as the NumPy ones, except since the idea is that it's sparse, you can pass it a density parameter, and then so it'll be sparse with the density that you give it. So here we're creating an n by n matrix with density 0.1, so about 1/10 of the elements will be non-zero. Okay. And then if you ever want to, you can use you can turn it back into a dense matrix with .to array. Okay, and be very careful that you do not use toDense because that will return a NumPy matrix and not a NumPy ND array. Okay. And also make sure that this matrix is not very big when you turn it. Okay. So something that you may have realized from a previous assignment is that explicit zeros in a sparse matrix are counted as a non-zero element. So anything that is a non-zero element which contributes to the runtime of a sparse matrix. Let me start the sentence over. So a sparse matrix, whenever you do an operation with a sparse matrix, the amount of time it takes to compute these operations is dependent on the number of non-zero entries in that sparse matrix, right? And if you have an explicit zero inside your sparse matrix, that counts as a non-zero entry. So for example, here, if I create a diagonal matrix where the diagonal elements are 0, then I never imported. Then the number of non-zeros here is going to be 3, even though the entire matrix is 0. So we could say a.toArray. The entire matrix is 0, but as far as SciPy is concerned, there are 3 non-zero elements in here. Okay, so just be aware that when you create these matrices, if you pass along 0 elements when you're creating these matrices, it will count them as non-zero and you won't get the performance that you want. Okay. So now, here we can breeze through a lot of stuff because they're the same as NumPy. So you can convert your matrices to different types in SciPy exactly the same way you would do it in NumPy. You can access elements the same way you would do it in NumPy. The only caveat is that certain sparse formats do not support indexing, but CSR and CSC do. So, but in the end, you just convert to a CSR if you ever need to access things inside your sparse matrix. You can do Boolean array indexing, you can do integer array indexing, you can do everything that you did before. It's just a sparse matrix. So in the background, it's exactly the same. Or, well, not in the background. In the front end, when you're indexing into these matrices, it's exactly the same. And so here's another same example, creating a one-hot encoding, but this time it is sparse. So here again, we create the vector of non-negative integers as our random vector of labels. And then here we do the exact same thing, except now we take a sparse identity matrix, convert it to CSR format so that we can do the indexing, and then we pass it the list of labels. Okay? And then this should come out with exactly the same 2 array. Yeah, it comes out with exactly the same thing. But now it's sparse. So if you have a ton of examples and you want to make it into a one-hot encoding, you might consider doing this instead of the normal dense one. Yeah?
So if we have like explicit zeros in our matrix,
Mhm.
how do we sparsify it? We have to like do 2 CSR?
So there is a function in SciPy that will drop all 0 entries in your sparse matrix. But in general, this is a very computationally expensive thing to do because you're basically recreating the matrix from scratch again. So like what it does is it goes through the same process that you would normally do to create the matrix. It just does now a check to see if it's 0. And so recreating the matrix is pretty expensive. So you want to do it as few as possible, basically. My suggestion would be make sure you don't include any non-zeros in the beginning, and then if after some math iterations, you do matrix multiplications and stuff, and now you happen to have some zeros, then, well, that's okay. Don't worry about it too much. But if you start off with a lot of zeros, then you've got a problem. Right? If you start off with a lot of zeros that you shouldn't have started off with, that you could have eliminated immediately, then you should consider rewriting your code to not actually put in these 0 entries. Does that make sense?
Well, but let's say if you initialize
Yeah.
the matrix, and then if you do 2 CSR, does it like automatically get rid of the 0?
I do not know for that particular example. We can find out right now. A.2 CSR dot number non-zeros. It works. So you turn it to CSR and it looks like it drops everything. That is 0. Right? Sanity check. Yeah. So it does. So I learned that today too. You turn it to a CSR matrix, it will drop the non-zero elements. All right, any other questions? Okay. Okay, so here's another example, which is scaling, again, from the same as NumPy, we want to scale the rows and columns of a 2D sparse matrix. Sparse matrices in SciPy, unfortunately, don't really support broadcasting with like NumPy arrays. So what you would want to do instead is just multiply by a diagonal matrix. So if you take a matrix and you multiply it by a diagonal matrix, that has exactly the same effect as scaling the rows or columns. Whether or not it's the row or column depends on whether you multiply on the left or you multiply on the right. So if this is new to you, just like write it out in an example. You can write down a matrix and then write down a diagonal matrix and do the matrix multiplication, and you'll see that it actually does the scaling. So that's exactly what you do here. You take the matrix and you multiply it by a sparse diagonal matrix. And so since this is a sparse diagonal matrix, this is very fast and it has the same effect as scaling the rows and columns of your sparse matrix. Something that I didn't mention before is that I could use the dot here instead of the time symbol, because for sparse matrices they mean exactly the same thing. Because sparse matrices don't have this element-wise broadcasting operation, so they both mean dot. But in NumPy, one means broadcasting and one means dot. I'm really sorry if you mix this up, but that's just how it is. Okay, so does that make sense? So you'll probably find something like this to be very useful on your assignment, because I think you'll need to scale rows of a sparse matrix. And then you can do the same thing as before, which was creating blocks, combining blocks of sparse matrices together. Use exactly the same H stack and V stack. The only difference is now you call it from the sparse library instead of the NumPy library. They also have the BMAT. And then you have the same matrix, and matrix vector multiplication. So you can take a sparse matrix, multiply it by a dense vector. You can take a sparse matrix, multiply it by a dense matrix. You can take a sparse matrix, multiply it by another sparse matrix. So all of these operations where you do a sparse matrix first and multiply it by something, they all work. Okay. And here I mentioned that these are actually equivalent. So the A dot B is equivalent to A star B when A is sparse. Okay. Now here is where the headache comes, which I am really sorry, but this is just the state of Python scientific computing. Which is when you try to use these SciPy sparse matrices, with NumPy matrices, everything is fine as long as you're using the SciPy operations when there's a sparse matrix. So NumPy operations work very well within NumPy. So NumPy dot something will always work when you pass it to NumPy arrays. But then if you try to pass a NumPy function a sparse matrix, NumPy does not know how to deal with this. Or it will try to deal with it and it'll do something completely weird that you didn't expect it to do. So for this example here, we're going to create A. A is a sparse matrix. B is a dense matrix. And here we do, the example that we know before, which is A dot B transpose. So A is sparse, B is not sparse, so that works. Okay. Actually, yeah, let me just show you for effect. Yeah, so we have this, and this works. And the result is a dense matrix because as soon as you multiply by a sparse by a dense thing, then the result is automatically dense because of the dense matrix, so they don't even bother returning a sparse matrix because it's going to be sparse. And then now here, let's see. Yeah, so here we want, if we try to flip the order of this, so now we want to do like B transpose dot A. The dimensions match, but this is not going to do what you think it does. Does anybody know what this does? So here the A happens to be in COO format, okay? And so what this ends up doing is if you try to write this, then you end up with this 2D array where each element is a sparse matrix.
Very useful.
And so I looked into this for a while, and I think I figured out that what it's doing is that it's doing B Kronecker product A.
B what?
Kronecker product. So cron. If you're familiar with the cron operation, what it does is it takes every element of the first one and multiplies it by the second matrix, and then puts them all together in a giant block matrix. So that's what it's doing right here. For whatever reason, so this is why you have a 2D array. It's the same size as B, and every element is now the sparse matrix where A, the sparse matrix has been scaled by that element in B. We might use Kronecker products later, but I don't think it's likely. But it's just the point is that it's useless. Okay, so you don't. So at worst, it doesn't even tell you that there's an error. I guess it gives me a warning here, but it goes through and does the computation anyways, and it's pretty useless. If instead A was in CSR format, then it doesn't give me the error, but it still does the same thing. Okay, so the point is if you take a NumPy array and you try to dot it with something, I think on my machine at home, it actually just throws an error when you try to dot it with a CSR format. So your results will vary wildly based on whatever happens here, okay? So if you have a sparse matrix, always do the operation from the sparse library. So the way you would do that is, so in this case here, I just actually, if you wanted to do B transpose A, then you can take the transpose, you can take the transpose of that and then distribute the inner transpose across the two matrices, which flips the order. So then we have B transpose A is actually A transpose B transpose. Does that make sense? It's like, recall your linear algebra. So flip the order and do the transpose. And so now we have the sparse matrix in front that's calling the dot operator. And then this one will work as normal. Okay. Okay. Yeah. And then here, again, we have, this is just to show you another thing that happens when you try to throw sparse matrices into NumPy, which is, okay, so we're going to take the sparse matrix and we take this dense matrix here, and we try to use the NumPy.multiply, right? So we try to do the NumPy.multiply, you think, okay, it'll do element-wise multiplication of the two matrices. Doesn't seem too hard because if one is sparse, then most things should be 0, right? But actually, as it turns out, NumPy just completely drops the ball on this, and we get the same Kronecker product. which is not at all the element-wise multiplication. But instead, if we use the SciPy's version of multiply, so then we take the sparse matrix and we do the A dot multiply, that B, then we get the normal thing. So as array. Is it not as array? To array. There we go. Okay. So if you have a sparse matrix, always do your operation from the sparse library until it's dense. And when it's dense, then you can do whatever you want. Okay. All right. So this all sounds like a pain and all, but it's actually very, very reasonably possible for this assignment to write everything without assuming anything about the sparse or dense structure of your matrices. That's because Python likes to do this thing called duck typing, which works for all the operations that you need in this matrix for this assignment. Okay, so also this notebook, I'll post it on the website in case you're furiously typing stuff here. So the idea here is that you can call functions that work exactly the same in both libraries. Okay, so here we're going to create A1, which is a sparse matrix, and A2, which is a dense matrix, and then just a vector B. I didn't say this explicitly before, but in general, vectors are perfectly fine to have dense because you're not really going to have any vector that's going to be extraordinarily huge in almost all cases. When you do have a vector that's like extraordinarily huge, then you'll find out that you probably shouldn't do it. But for all intents and purposes of this course, I don't think we're ever going to give you a problem that is that big. The issue really comes in matrices when you now have that vector multiplied many times as many rows. Okay, so back to here. Here we can write the exact same code that just does the dot product of a matrix with a vector by just calling dot from the matrix. So if the matrix is sparse, then it'll do the sparse one. If the matrix is dense, then it'll do the dense one. And you don't have to worry at all if it's dense or sparse. So for example, in your SVM assignment, you can take your feature matrix, multiply it by your parameters. Now, if you did this in a not so good way, you would take the parameters dot to the feature matrix, and that might give you problems because the feature matrix is either sparse or dense. But if you take the feature matrix dot the parameters, then you'll get the correct behavior no matter what type the feature matrix is. Okay, and then another example that you may find particularly useful is that you can also do type agnostic scaling of your rows by doing this sparse diagonal multiplication. So you remember before when we scaled the sparse matrices, when we scaled the rows of every sparse matrix, when we scaled the rows of a sparse matrix, we multiplied on the left by a sparse diagonal matrix, right? Remember that? That works actually for NumPy arrays as well. So, it doesn't really matter if it's a NumPy array or if it's a sparse array, but you can just multiply on the left by a sparse diagonal matrix and that'll scale every row, right? Because it's this sparse matrix knows how to deal with everything. So. And then, another example, if you want to take the max of matrix, you just call dot max instead of using like numpy dot max. If you use numpy dot max, then now you're throwing this into the can of worms where now you're assuming that the matrix that you're giving it is going to be from numpy. So instead, we just take the matrix. It doesn't matter if it's sparse or dense, and we call it dot max, and that doesn't matter if it's going to be sparse or not. Okay, so for the SVM assignment, you can do it all with these operations. And you shouldn't have to worry at all whether or not it's sparse or dense. Okay. If you do, then I guess it doesn't really matter if you do make a case for it, but it comes out a lot cleaner if you just don't worry about it. Okay. Okay. All right, the very last thing. So that would cover everything that you need to know in the cross-validation notebook and in the MNIST notebook. The last thing is for naive Bayes, which I think the only new thing there is you need to start using scipy.stats, which is basically a library that has a bunch of probability distributions in there. So it has a whole bunch of random variables with many, many, many different types of random variables. I think Zico discussed a bunch of them in lecture, right? Yes? No? Yeah. Okay. So yeah, he discussed a bunch of them. There's a ton of them. like, and by a ton, I mean a ton. Like, these are all different random variables, okay? Okay, so these are all the different random variables. So if you need to pull from a distribution, just pull from these random variables, because it almost certainly has it for you, except for the categorical random variable, which is implemented in like NumPy as like numpy.random.choice. But yeah, basically, if you need a distribution, you fetch it from here. I think we tell you to get the normal distribution from here, so you don't have any problems with like trying to code it yourself. Though you can code it yourself; it's not terribly hard. So like just here's like an example. You would import it with. Did I forget the import somewhere? I think I lost the imports. Oh no, it's down here. Okay, so here's just import scipy.stats. And then you can get every single random variable with just, that Bernoulli one, dot Bernoulli, and then you can get the PMF of it. So remember the probability mass function. Then the first argument you give it is the value at which you want the PMF at, and the second argument is the parameter. So then this is what's the probability of 0 given the parameter is 0.2. If you want, so then you can calculate probability densities and probability mass functions with this. You can also create random variables. So what it does is it sort of freezes the parameters so that you don't have to keep specifying the parameter every time. So this creates a Bernoulli random variable. And then from that random variable, you can call the same PMF function. And now you just have to supply it, what's the probability of 1 or what's the probability of 0. And then I think all of them also have this log PMF, which will compute the log probability, which is usually a lot more stable and easier on your machine when it's trying to compute the numerical accuracy. Okay, and then here's another example. So that was a discrete distribution. The only difference between the discrete and the continuous distributions is that the continuous ones will use PDF for probability density function instead of probability mass function. Otherwise, the usage is exactly the same. You pass it the value you want to calculate the PDF at. You can for the Gaussian one, you can optionally pass it a different mean or a standard deviation. I think they name it lock and scale for whatever reason. But if you just look at the documentation, they say the mean is lock and the standard deviation is scale. I don't know why they didn't just call it mean and standard deviation, but that's what they did. You can create random variables, and then from that random variable, you can calculate the PDF and the log PDF. Some useful things that you may need in the future is that there's also a CDF function, which is the probability that random variable is at most that value. There's the inverse CDF function, which is the inverse of the CDF function. And so here, this is just a simple plot I'm just taking a range of values between the inverse CDF of something very small and the inverse CDF of something really big. So this will give me the two extremes of the values, the two extremes of the values the random variable can take, and then just plotting them, and you get your your normal random variable. It's not standard normal because I gave it a different mean and variance, and then here you just plot. It's another plot of the CDF function, things like that. But that's the end of the notebook. So, any questions, comments, concerns?
So you mentioned that the notebook will be shared on the...
Yeah, I'll post this notebook, yeah. And if this recording worked, then the recording will also be online. Which it looks like it's working. Okay. Anything else? Was this helpful?
Yeah.
Okay.
Could you... there's something that I wonder, it's kind of maybe a little bit off this topic, but there are cases where I wrote some tests, wrote some code locally with the sparse matrices and the arrays and everything, and it either ran or didn't run for some reason. And then when I upload to Autolab, I receive errors that I didn't receive locally. So I don't know, maybe depending on type or something, I tried to test it with the sparse matrix type as well as the dense matrix type. And maybe the Autolab's NumPy version and SciPy
Yeah. So the only thing that I've seen that has been different across machines is as soon as you start trying to pass SciPy sparse matrices to NumPy functions, then sometimes it'll throw an error, sometimes it won't, and sometimes it won't throw an error, but it'll do something crazy.
Yeah.
So like, like here it was doing the Kronecker product of the two matrices for whatever reason, which, if you do that on AutoLab, actually, then it'll try to do a Kronecker product of your 10,000 by 100,000 feature matrix, which means it's not going to copy that 10,000 by 100,000 feature matrix for every single thing that you're multiplying it by in the other matrix, which is going to definitely cause it to just die. But the only inconsistencies that I've seen is when you pass sparse matrices to NumPy functions. So like at home on my machine that's not this laptop, actually some of these functions just threw an error and told me, you can't do that. But then I guess on this laptop, it worked, but like it didn't actually work. It did the Kronecker product, so it was just completed, but like, it didn't actually work. So, but I have not seen a case where it actually does the right thing yet. So it might be running locally on yours, but you might also just be doing the Kronecker product, and it might just,
No, like, yeah, I see what you mean. Like, I try to print like intermediate results and see that, so I was wondering whether.
Yeah, so that's actually, that's the best thing I think you can do, is when you're writing these functions, is to just, you saw how like here I was just writing the functions, I was like doing x dot, and then you could write dot theta, plus like 500, and then see if this runs. And if it runs, then great. But if it doesn't, then you've immediately found out that,
Sure, yeah. That's what I'm trying to do.
Yeah. Okay. If there are no further questions, then that's the end of recitation. All right, thank you.